Hello, my students. This is Mrs. Gerhardt, and this is a concise refresher and teaching, if we need it, on Vesper Theory. This video will remind us of the next step we take after Lewis dot structures. Lewis dot structures are incredibly useful. They allow us to really map how the bonding is occurring. Do we have a single, double, or triple bond? Are there any unshared pairs? Is the octet being satisfied? Great knowledge. However, their limitation is they seem to portray molecules as flat. We know our world is three-dimensional. So what Vesper theory allows us to do is take the correct Lewis dot structure and then predict the 3D geometry. I'm going to switch out to the document camera because I will refer in a moment to the pages in our packet that address Vesper theory. So what is Vesper theory? Well, as I have here for us. Well, first, what does Vesper stand for? Valence shell electron pair repulsion theory. We know that pairs of electrons, shared electrons, repel each other, and that increases a higher energy situation. So to minimize energy, the bonds will position themselves and the non-bonded as far apart as possible. That creates a lower energy situation. That's where our geometries come from. There is an incredible animation, a kind of interactive site. I'll just play around a little bit for you, by the University of Colorado, PhEt. And this is how we get our shapes. So if we have our center atom, and there's two bonds, and the bond could be a single, double, or triple. Well, then this is going to position itself as far from this as possible. Even if we try to bring it over, it'll repel away. This gives us what we call a linear geometry. And the linear geometry has 180 degrees between this element, the middle element, and the other element that is participating. All right, well, what if we have a third area of bonding? I'll bring in a single bond. Well, do you see, as we bring this in, it naturally will repel these away, but these are repelling each other, and also this. This as far apart as we can separate these. Now, if you take a look, though, we're still flat. This is our trigonal planar, and all of these are separated by 120 degrees. Well, let's bring in a fourth, and this is when we get three-dimensional. We normally refer to this as a tripod. We have our three base bonds, and then, what you might use a tripod for, holding a camera and such. The geometry is tetrahedral, the bond angle 109.5. Our molecules can also have a total of 5 areas of bonding. Now, do you see, if I try to bring this, let's see. We see how it's fighting me. All right, here is the trigonal planar. These are separated by 120, remember? All right, but we have that trigonal planar, but then a 180 degree bond angle that is 90 degrees between the top and this plane, 90 degrees, and so on. Trigonal bipyramidal is that geometry. And then if we would bring in one more, everything is separated by 90 degrees, and this is octahedral. And we can move all this around. See, they try to get close, but the repulsion will balance out. But we know that we don't always have bonded atoms. We can also have, I'm just going to remove some of these, lone pairs. So if we have our center and it has 3 bonds, that's trigonal planar. However, what if one of these is a lone pair? We can't see the lone pair. We see bonded atoms, not lone pairs of electrons, but those lone pairs impact the geometry. Because this is a lone pair, we don't go back to linear. That lone pair actually causes more repulsion between these shared electrons. So we no longer see the peace sign, the Y, whatever we want to call that, whenever this lone pair is a bonded atom. Okay, that's what we would call trigonal planar. But whenever we take away but have a lone pair, now the electron geometry is still trigonal planar, but the molecule we call bent. Because we just see this boomerang, we don't see the whole thing because we don't see unpaired or unshared electrons. And this bond angle is not 120. It will be less than 120. Okay, let's just show. We know when we have 4, that's our tripod. That's tetrahedral. But what if we bring in a lone pair? Look, now it's kind of a squished tripod. And these are going to be closer, not 109.5 bond angle. So it's trigonal pyramidal. What if 2 of these are lone pairs? Well, then even though the electron geometry is tetrahedral, we're just going to see the boomerang, that is bent. And this bond angle would be less than 109.5. All right, so in our packet, you first will see, the theory behind Vesper. I have some visuals. Here is how we would draw those geometries. If it's a solid line, it means it's flat with the paper. If it's a shaded in triangle out, it's coming out of the page. If it's a dashed, it's going into. Here are our bond angles. So if I can just explain tetrahedral and why do we draw it like that? Well, remember tetrahedral is our tripod. Yeah? Well, if we hold this just so, then we have our center element, whatever that would be, and a bond going up, and I'm going to make these flat, and a bond to the bottom left. But then this comes at you. So to show it's coming out of the paper, we draw a shaded in triangle, and then going away, we do these series of dash lines. And then you would put either your lone pair or your elements there. For example, methane. Methane, carbon with 4 single bonded hydrogens. Well, carbon is in the center, and then we would draw the tetrahedral geometry just like that, bond angle 109.5 degrees. Ammonia. There are 1, 2, 3, 4 areas of electrons. So we still draw it as tetrahedral. We draw the electron arrangement. Now, for a total of 4 electron areas, you have the freedom to choose where you would like to put your lone pair. So since in my Lewis dot, I put them there, I'll put my lone pair there, and then my hydrogen, hydrogen, and hydrogen. However, because this lone pair causes more repulsion, this bond angle will be less than 109.5. We never have to know specific, just that it will be less. It's not called tetrahedral, it's trigonal pyramidal. And we need to memorize all of these terms. Tetrahedral, the bond angle that is related to it, and then if there's a lone pair, what the new geometry will be called, and the impact of that lone pair on bond angle. Water. So we have our oxygen with 2 lone pairs and 2 single bonded hydrogens. So it doesn't matter where you choose to put your electrons, maybe there and there, and then your hydrogen and hydrogen. But this geometry is bent, and this bond angle will be less than 109.5 degrees. That's probably going to be, further from 109.5 than 1 lone pair. However, we just have to say less than. So where this may be, 108 or 107, this is probably going to be closer to 105. So, but we don't have to know that specifically. All right. So, also, if you have pairs of electrons on your bonded elements, you need to show that. All right. On page 28 in your student packet, here is a layout. And so this may be your tool for memorizing. Now, steric number is the number of electron areas total. If both are bonded, linear, 180 bond angle. But even if one of these is a lone pair, you can't put a lone pair any further than 180 degrees. So no matter if you have 2 total electron areas, it's still linear. But here's 3. If they're all bonded areas, trigonal planar, if one pair is non-bonded, it's bent. Angular is a little bit of an older term. Here we go with 4, tetrahedral, trigonal pyramidal, and then bent with 2. Trigonal bipyramidal, usually seesaw, we're going to see more often, then T-shaped. Now, of course, linear, but I'm highlighting the geometries that we are responsible for knowing, memorizing, may come our way on our unit test as well as the AP exam. So what we need to be able to do, ladies and gentlemen, is move from Lewis dot to Vesper structure. Redraw it, definitely name it, and predict bond angle. So for example, nitrate, we're focusing on the center element unless specified differently, and we'll look at those in class. So around nitrogen here, I have 1, 2, 3 bonded areas, no lone pairs. So then I know it'll be my nitrogen, and you have the freedom to choose. Whatever is in your Lewis structure needs to be respected in the Vesper. So a double bond. Now we know these are going to be different lengths, but you don't have to show them as different lengths unless the directions tell you. We know double is shorter than your single. No lone pairs on my nitrogen, but I must show. And I'm drawing my best to show 120. I'm not going to get out a protractor and actually measure that. But this would be trigonal planar and bond angle of 120 degrees. Here we have 4 total areas of electrons. That's my tripod drawing. However, 2 are lone pairs. It is a bent geometry, not tetrahedral, but I draw it like it is. Your lone pairs, just put there, and how about there, and then your hydrogens. And we know this, because of the lone pairs, will be less than 109.5 degrees. No brackets needed because it's not charged. And what about here? We have a total of 1, 2, 3, 4, 5 areas. Okay, that's going to be our 1 up, 1 down, 1 in the plane. This is our trigonal planar in the plane, right? And then 90 and 90. Now, here it does matter where we put our lone pairs. Our lone pairs will be placed on the plane because then they're 120 degrees away from another lone pair, 90 degrees. I know it seems like we would want to put the lone pair here. I'm sorry, that's how I should have said it. If we put the lone pair here, it's 90 degrees to 3 other areas of electrons. But if we put it here, it's only 90 degrees to 2 other areas. So the lone pairs are always favored to be on the plane first. Now, this geometry is called T-shaped. I'm going to favor putting the lone pair here and here because then how I've drawn it, it looks like a sideways T. But you could put the other lone pair there. You just have to use your imagination to be able to see the T. All right, so this will be T-shaped. All right, so how do these electrons impact the bonding? Well, this is going to try to push this closer to this, and this is going to try to push this closer, so this bond angle isn't changed, the bond angle of 120, but this might be a little less than 90. And so this might be a little less than 180, just ever so slightly, ever so slightly. If you went ahead and said less than 120, that would be okay, but we're usually not including lone pairs in a bond angle because they're just bonded to the center, really, or owned by the center. All right, so I hope that gave a good kind of overview. Practice in the unit assignment. I gave us also just a table of just, the terminology. If just seeing it this way will help your learning. And, ultimately being able to put these rules in place that are on page 31 in your packet and being able to answer questions like 1, 2, and then eventually number 3 are what we need to do with this knowledge. As always, email any questions or concerns my way. Thank you, ladies and gentlemen.